Hello, my name is Mallory Molina, and I am a postdoctoral researcher at Montana State University. Today, I will be presenting my work on outflows from a radio-selected AGN in a dwarf galaxy. Massive black holes in dwarf galaxies provide strong constraints on the formation and evolution of supermassive black holes, but are notoriously difficult to detect. Recent work by Ryan et al. 2020 used high-resolution VLA data to search for radio emission consistent with AGN activity. They identified black hole candidates in 13 galaxies, but most of them did not show AGN-like emission in their SDSS spectra. I am presenting my follow-up work on this sample using integral field unit, or IFU data from Gemini North. The Gemini IFU data have a resolution of 1 arcsecond, which is 3 times smaller than that of SDSS. My goals for this project are to confirm the presence of a black hole in the observed objects and to study the effect of that black hole on its host galaxy. For this talk, I will focus on the object J12203020. I'm showing the decal image of the galaxy on the left, the VLA observation of the galaxy in the middle, and the SDSS narrow-line diagnostic diagrams on the right. We note that this galaxy appears star-forming in the 3 arcsecond SDSS spectrum. However, we do find strong evidence for a black hole in the Gemini IFU data. In the 1 arcsecond radio source spectrum, or black hole spectrum, we detect the AGN coronal line iron 106374, which is known to be produced by shocks created by outflows from or photoionization by an AGN. Furthermore, we detect broad H alpha emission that is only seen in the radio source spectrum. Finally, we find an enhanced L1 feature centered on the radio source, which could indicate an outflow. However, the BPT style diagrams do not definitively show AGN photoionization as the dominant energy source. So the top panel is showing the O3 over H beta versus N2, S2, and O1 over H alpha diagrams, where the black diamond is the spectrum of the black hole candidate, and all of the other points fall outside of that region. The physical position for these apertures can be seen in the cutout below. Clearly, the N2 and S2 diagrams do not show line ratios consistent with AGN photoionization for most of the apertures, while the opposite is true for the O1 diagram. We do note that as O1 is not strongly produced by star formation, it is likely less contaminated from the host galaxy than that of the N2 and S2 diagrams, which could make that diagram more reliable. Regardless, there is still no one photoionization mechanism, neither AGN nor hot stars, that can clearly describe all of the observed data. Given this ambiguous result, we also included shocked emission diagrams in our analysis. Here, I'm presenting the shocks and shocks with precursor models for O3 over H beta versus S2 over H alpha. Shocks here mean a simple shock front is collisionally exciting a gas, while the shocks with precursor indicates that the shocked gas creates photons which travel upstream and pre-ionize the gas in front of the shock wave. The model grid shown in magenta and black cover a range of metallicities, densities, and velocities as labeled, and the points are the same color scheme as the previous plot. After looking at the N2, S2, and O1 narrow-line ratio diagrams, we find that the black hole spectrum is consistent with a combination of shocks and photoionization, while the off-nuclear spectra are consistent with shocks and/or shocks plus photoionization. This means that both shocks and photoionization are significantly contributing to the overall narrow-line emission. Therefore, relying on simple photoionization models will not clearly detect the AGN activity in this object. So in summary, we're presenting the first of our follow-up of the radio survey conducted by Ryan et al. 2020. We confirmed the presence of a black hole in J12203020 through a variety of methods. We also note that shocks and photoionization both contribute to the narrow line emission in this object, which create ambiguous results in the traditional BPT diagrams. This may mean that radio surveys are probing a lower accretion rate population of black holes in dwarf galaxies than optical surveys alone. Thank you.